sound. That's earthquakes. And today's the 18th. New page. Here we go. 18, 2, 10, 11. Good morning, Teresa. I hope you're well, keeping your sanity out there, not going too crazy. Zach, good morning. Okay, half my class is there. I love it. Let's go for 100%. For the most part, yes. Well, it might be getting a bit warmer now, so maybe we'll actually start to see some crocuses or some sign of spring outside. That would be nice. I am ready after a, pretty intense couple of snowy weeks. The snow was kind of nice too, but I'm ready for some, some spring feelings, as it were. Yeah, let's see. Well, let's go ahead and tell you what's going on. We're going to finish up with the physics of the ear today. I'm going to draw some of this today because I know it's hard to see it all, okay? But essentially, we're going to do the inner part today, the last little bit. And then, I'm going to pull that off, might be easier to see. We're going to do the last little bit today, and then talk a little bit about ear protection and talk about bats and earthquakes, which would be your next couple assignments as well. I think I assigned you something. I assigned you the video. Did either of you get a chance to watch the video? And Zach or Teresa, do you have questions on the video or what caused things? Good morning, Ellie. Questions on the video or what caused the bridge to collapse? Well, if you haven't watched it yet, it's the Tacoma Narrows Bridge, which collapsed basically back in 1941, I think it was. And the video is pretty cool showing that. Okay, that's fine. If you got questions, just write me, all right? We're a small group. I want you to feel like you could write me with it when there's anything you want to ask about. And then Sophie's here. 100%, yes. Okay, so welcome everybody. Let's go ahead and finish up the ear and the physics of hearing. And we'll talk a bit about bats and earthquakes today because I have two assignments that I'm going to have you do on bats and earthquakes that practice with waves. Yeah, okay. And waves are just so important. So if it seems I'm spending a lot of time on it, well, I am. It's like a physics basic. Okay, so I'm going to draw the last part here. When last we met, we talked about the compression of waves coming in to your ear canal, right? And the cool thing about the eardrum, did I tell you this? It undergoes a forced vibration. In other words, the drum is forced to vibrate at any frequency it hears within the range of human hearing, okay? So it's forced to vibrate and it bangs against these three little tiny bones. So this is just a review yesterday. These little tiny bones are levers, so they increase the force of the sound. So actually it makes the sound louder for our brain. So the levers make it easier for our brain to hear stuff. Then we get to this inner part, and this is what I'm going to draw. It looks like a snail. In fact, the German word is Schnecke, and in English we call it the cochlea. We'll draw that along with this goofy like circle things up above. We'll see what those are as well, okay? All right, so I'm going to draw that a little bigger on the board. All right, not that much bigger because my board's pretty small, but you get the idea. So here we go. I'll try and draw it like they did there. So I think I'll draw it like this. I'm going to draw that extra big. And then I'm going to sort of draw this coming off. And then we're going to have this and this. And this. That's one of the better times I've drawn it. No, it's actually not. Let's fix that. Okay, now it's better. Yeah, that's not bad. Okay, and then we get over here, and I don't really care except that the last thing to hit here is the stirrup. Actually, it looks like an upside down stirrup, so I'm going to draw it upside down. You know, a stirrup, like the thing you put your feet in if you're riding a horse? Well, that's kind of the last lever, the last bone, okay? And this part is called the middle ear, by the way. The outer ear you can guess, and this is going to be called the inner ear. I'm not really making this to scale. I'm making it big so we can see it easier. Okay, so remember the I'll do the wave in red. Yeah, I don't know if you were there or not. Yeah, you did miss it. So you want to go watch the video there, Anne-Sophie. So here comes the wave, bum, 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 bum. And now it hits this sac, this huge sac. I'll close that off. And this is filled with fluid. It's filled with ear fluid. It's very watery. In fact, it's mostly water. But you guys have some ear fluid. We'll see why that is. It's got a couple of reasons. Anyway, so that's the new medium. That's what the wave's traveling through. So here we go. So the waves go through here. And we're going to see what happens here as they go through this part. I'm just going to draw them going like this. Anyway, this big snaily thing is called the cochlea. C-O-C-H-L-E-A. Cochlea. And yeah, okay, so here comes the wave. Here comes the compressions. Bump, 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 bump. Oh, by the way, you could draw a little bit part of the end here too. That's called the auditory nerve. It goes to the brain. So you learn a little anatomy here in physics as well, okay? Okay, right. So here's the cool thing. Maybe you know this already. Okay, that's fine. Just watch the video. Yeah, okay. All right, so here we go. In the cochlea, especially in the inner part, there's these little, they're almost like hairs, but they're not hairs, okay? They're called cilia. I'm going to call them hair-like features, but they come up like this from the edge of the layer of the cochlea. And I'm going to stop drawing them there, but they go on a while. Anyway, these things, here's how you spell cilia. These things are extra cool. The wave comes in and Each of these little cilia has its own natural frequency. Now, if the wave matches that, guess what they do? In fact, I'm going to write that down below. So if the sound wave matches the natural frequency of a cilia, the cilia, all right, see if we can fill that in. Maybe we got some already. No, we don't. Okay, so let's fill that word. So it's from last time, so 3 of you should know it. So if sound wave matches the natural frequency, we talked about this like with an item on the car, or as it turns out with Tacoma-Narrows Bridge. Okay. What else did we talk about it with? I can't remember now. Thank you, Ellie. Yeah, so it resonates. So it's going to go like this. Oh, I hit the natural frequency. The cilia starts to resonate now, which means to vibrate with a high amount of energy. It takes in a lot of energy from the sound if it's got the same natural frequency. So it resonates. And of course, and by the way, there's lots of hairs. It's not like there's one for every frequency. There's several for every frequency of sound. Okay. All right. So the little hair-like features, the cilia, are connected to the auditory nerve ultimately. So I'll just say this sends the brain a message to say what frequency you've heard. I'm going to read that off because I know I'm getting to the bottom of the board, but I don't want to erase yet because I don't want to erase my drawing. So here we go. So after resonates, this sends the brain a message to say what frequency was heard. Okay, so ultimately we get to the auditory nerve and that gets sent on to the brain. Now, of course, you and I hear lots of complex stuff. You know what I'm saying? So human voice has many frequencies mixed in with it. So you'll have several hairs that will go at the same time and resonate at the same time. Anne-Sophie is a very robust vibration. Resonant is a very robust vibration. So it's got more energy than just a normal vibration. Resonating, it means it's vibrating a lot. Okay, so you'll get lots of frequency information sent to your brain, okay? Or if it's a tuning fork, you'll get one frequency, right? Because that's what tuning forks have, is just one frequency apiece. So you just have the hairs that have that frequency will vibrate. So what I'm trying to say is your ears are cool. They've got 2 big physics ideas. One is the eardrum, and that thing undergoes what's called a forced vibration. It has to vibrate at whatever sound hits it. That's actually 3 cool things. The bones that increase the loudness or amplitude of the sound, right? And then finally, this cool thing with the cilia that resonate if the sound matches their natural frequency. Okay? Yeah, exactly. There you go. So you've got, Anne-Sophie, something with just one frequency. Yeah. And of course, when you tune your violin, you're tuning to match that frequency. I wish I could do that demo, but I don't have that here. So I'll not do that. Okay, I want to talk about hearing problems. So I hope you have the ear drawn because I got to erase it now. So I got a little room up here. Oh, hell, I didn't want to erase it yet. Dang it. Okay, the three, it's not hearing, but the three loops, I just erased them, but what do those do? Who knows? It's not having anything to do with hearing. They're called the semicircular membranes. So what are they for? What are the semicircular membranes? You've got one, and they're like this. They're like, eh, eh, and eh. They're like in three planes. They're like in three planes. So you guys are probably at X, Y, and Z now in math class. So imagine I've got one of these. There's X, Y, and Z. I got one of these going this way. I got one of these going this way. And I got one of them going this way, so to speak. So I've got them in three dimensions. So do you know what these things do? A lot of times athletes know what these things do. They're very important in your ears, but they have nothing to do with hearing. They have to do with, starts with a B, they're for your balance. If you get hit on the head really hard, you're going to have a hard time with your balance because the fluid is also in the semicircular canals. Ah, okay, and Zach just got it in, balance, right. So, you've ever used a balance to like hang a picture, a Vasavaga, okay? It's got little bubbles in it. Well, these don't have bubbles, but they kind of work similarly, except instead of one of them, we've got three of them. Why? Because the world is three-dimensional. Isn't that cool? Your ear has three of these. So it's got one in this direction, one in this direction, and essentially one in this direction. So it gives us a sense of what is right, what is the right way to go up, so to speak. So it really helps with your balance. Yeah, exactly. Good. Thanks for jumping in, everybody. Yeah, so if you have a head injury, it takes some time to reestablish that balance because they are shocked and take a little time to come back so you get your sense of balance. I have a colleague who retired and he had a strange illness that affected the sense of balance, and he had to really learn how to walk again because the sense of balance was gone for a while due to problems with the three semicircular canals. Okay. It's weird that it's on the ear, but it just is. Okay. So, but it doesn't have to do with our hearing, but instead our sense of balance. But lots of physics in there too, as it turns out, huh? Okay. There we go. Let me erase that now. We actually are set with that. Okay. Older folks like me, like your parents or grandparents. What happens to the cilia as you get older? Can you guess? The little hair-like features. What happens to them as you get older? See if you can guess. Doesn't happen with every old person the same way, but it happens with most old people. What happens to the cilia? In a sense, they weaken. They don't deteriorate, luckily, Ellie. They don't like fall apart. Um, they they get more rigid. They're not as flexible as they used to be. Kind of like as we get older, our muscles are not as flexible. So to be like resonated the sound's got to be louder. You see what I'm saying? So old people have to have louder sound to have the cilia resonating. Or to put it another way, soft sounds won't do it. So quiet sounds are not heard. And now you know why. And interestingly enough, the sound that men tend, sorry, Zach, but men tend to lose their hearing more than women. Just the way it is. Women too, but men, it's even worse. And men often will lose their hearing in like the frequency, the high frequencies of their wife's voice, which I find always kind of sickly amusing. Uh, anyway, so like when my parents were older, quite a bit older, in their 80s, my dad said to me on the phone one time, he said, "You know, your mom's really been mumbling. She's been mumbling lately." Well, do you think my mom was really mumbling? No. My dad's ears were getting bad, so he couldn't hear her high voice anymore. So men tend to lose the high frequencies, okay? High frequencies, which is often for women's voices. Not wild? Yeah. What age does this usually start? It can happen at any age, but traditionally 50s, 60s, you know. So I'm starting to get in one ear. I probably need to get, well, what do some of your parents or grandparents have to alleviate this? What's the solution? Or what do I need to get, folks? What do I need to get? Especially for my right ear, I think it is. Yeah, thanks, Aunt Sophia. I need hearing aids. At least one. And hearing aids have gotten to be pretty advanced. There you go. Yeah, there you go. Your grandpa had them before your grandma. Typically, men get it first. Okay. Yeah, you can get implants too. Especially people that have like true ear problems, they could get cochlear implants. So new implants where the cochlea sits. But that's a different thing. We're talking about just something that sits in the outer ear, Teresa. So something like that. It's something you can take out before you take a shower or go swimming. Okay. All right. So what do? They're adjusted for each person. So they amplify sounds that are not heard well anymore. So they amplify, how about only? So where my dad bought his, they adjusted them so they amplified the high frequency sounds for him. They tested which ones, which frequency he needed. Okay, you need from 225 to 700 hertz or whatever, okay? And then they amplify those. The ones that do work, they don't amplify. So they're very exact now how they do this with you. And you can have them readjusted as well, your hearing aids. So that's a good thing. Okay, and I want to talk briefly about chainsaws. And other stuff. Blah, 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 blah. We'll fill that in a second. Question, comment first. Let's see. Yeah, they test your hearing first and then they fit you for hearing aids. Physically, they have to fit in your ear, and physics wise, they have to fit what you need amplified, what frequencies you need amplified. Yeah, probably so. Yeah. Yeah, good. Okay, chainsaws. I knew guys that cut their own wood in Montana, right where I'm from. Well, they're really loud, and some of these guys were stupid and they didn't wear any ear protection. So my point is, loud noses, loud noises can shock your cilia at a younger age so that you lose the hearing much younger. So loud noises, I'll just say they cause the cilia to become rigid even at a younger age. Well, how young? Sorry. Another problem place in Berlin is clubs. Now, I don't go to a lot of clubs, but I've been to a couple of clubs, and it was so loud where I was at, and I don't know if you've had this experience, but I came out and my ears were ringing. That's not good. If you do that often, even at a very young age, like in your 20s, you're going to start losing hearing. And this is a problem without ear protection. So I can only say this, and it sounds wimpy, but say you're going to a concert or something, you know it's going to be loud. You may want to consider at least putting in some earplugs to drown out a little bit of the sound just to protect your hearing. Because sometimes they have those decibels up. We haven't talked about the decibel scale. We should do that too. They have a decibel so high that it really does damage your hearing, you know? Can I make it darker? Yain, I can read it off, and maybe I can also, let's see if this will help. I'm going to adjust the studio lighting here and see if that cuts the glare. Does that help at all? Maybe it's less glary that way. I'll read it off again. So I wrote here, chainsaws and going to clubs. Loud noises cause the cilia to become rigid at younger ages. Right. So there's my warning. I know I sound like your parents, okay? But do protect your ears because you only have two of them. And once they're damaged, you're pretty much screwed. So be good to your ears and you'll hear for a lifetime. I know, it sounds cheesy. Let's talk about the decimal scale. Sorry, the decibel, not decimal. I forgot to do this with you before. And it's something we should probably know. There's so much to tell you in this course. Okay, so decibel scale. Named for, who was the guy who invented the telephone? So named for, and his name was not Deci. Who was the guy who invented the telephone? All right. Any guesses before I do? I know there's a time lag. Some of you might be typing furiously already. He did a lot of experiments with sound in the U.S. Mm-hmm. Yeah, that's good. That's good. Okay, name for Alexander Graham Bell. And by the way, there's still the Bell Laboratories in the U.S. today, which are research laboratories, also named for him. Bell Laboratories have come up with some other cool technology we'll talk about later in the course. Okay, right. Yeah, exactly. Exactly. Okay, so if I have like 0 decibels, and by the way, dB, it's small d, capital B, 0 decibels, that's like the threshold of hearing. Conversation would be like at about 50 decibels, okay? Above 80 decibels, which is like the sound of an S-Bahn approaching. All right, 80 decibels. S-Bahn approaching. Well, above 80, if it's for a long enough period of time, like hours, if it's just instantaneously, it's not a big deal. But you can get you can sorry, you can, yeah, okay, you can get hearing loss. Give you an idea here. Another one. If I go to like 120 decibels, now we're talking about either like you're 10 meters from a jet engine, or you're at a rock concert. Ha ha. Right? I'm on a highway to hell. Okay, so if you're at a really loud concert, you come out and your ears are ringing, you're not doing them any favors, especially if you do this really quite often. So it's a matter of not just the intensity, folks, but the amount of time that your ears. Let's say I'm at a job and I get 90 decibels of sound most of the day. That's not good. However, if I hear a firecracker at Sylvester, maybe it's not great, it's up here, but it's only for a very short period of time, and my ear probably has a chance to recover. So hearing loss is about intensity and time of exposure. So intensity, time of exposure affect hearing. There's a famous guitarist from my generation by the name of Pete Townsend. He used to play for The Who. He's got about 10% of his hearing left in both ears. Not much. Not much. A lot of rock concerts kind of did him in early in life. He lost his hearing. Yeah, all right. Good. Questions from you about hearing? Anything you want to hear? I feel like there's stuff I'm forgetting, but there's always more interesting stuff in this class. What I like about this class is we get to kind of sample the cream. There's a lot of cool physicsy ideas that I don't always have time for in other classes, but we can talk about them here. Right. Good. Okay. Let's go back to where I was. Okay, we're about up to that. Who was Antonio Musi? I have no idea. You'll have to Google him and see. Okay, right. I'll leave that for a second. I'm going to have you start to work on a couple of worksheets. And to be honest, I've sent so many assignments. Have I sent you the assignment yet on either bats or earthquakes, my people? Either bats or earthquakes? Have I sent you either one? I'm afraid I get lost sometimes in all the assignments I've sent you. I think the answer is no, but maybe somebody could just verify. You've had no assignment on bats yet and no assignment on earthquakes? I don't think so, says Zach. And Ellie says no. Thank you. Okay, so let's talk about the next two assignments I'm going to have you do. I probably won't meet with you tomorrow, but I'm going to have you work on this one instead. And the first one is on bats. And of course, they use ultrasonic sound. We know that. and it's going to talk about echolocation. So remember, bats are going like, well, here's the bat, right? Whee! And they go out and they hit a bug, burn, and the bug then causes an echo back, and the echo comes back, and the bat knows where to find the bug. And you're going to find using the wave equation, so you're going to use V equals lambda times the frequency a couple of times in that, but you're also going to use the old one that just says what? Velocity is distance divided by time. So you may use both of those in the activity. And we need to talk about milliseconds. You see, it's such a short period of time that the sound takes to get from the bug, that's supposed to be a bug back to the bat, that we're talking about milliseconds. So let's say, so I'm going to say here, what's a millisecond? Okay, so let's just say something. So 4 milliseconds, so it'd be ms, would be, and we got to move it like 3 spots, so it'd be 0.004 seconds. You know what I'm saying? I think that's right. So I got to move it 1, 2, 3. Yeah. So just so you know, reminder what milli is, because otherwise that assignment's kind of difficult. Okay. Yeah. And I think that's enough for you to do the bat assignment. So if it doesn't drive you batty, I'm going to send you that. I won't have it due Friday. I'll have it due next week sometime, so you have a little time to ask about it. A week from today, by the way, I think we have a training day, the teachers, so I don't think I have you a week from today. So yeah, I don't think you'll have any classes a week from today. Don't quote me on that, but I think that's what's in the school calendar. Okay, so that should help you do the BAT assignment. Let me think about anything else in that assignment that you need. Well, let me just go get it and take a quick look at it. I got a hard copy of it here. Okay, so when I send it to you, it's going to look like this. Okay, all right. Yeah, you should be able to figure that out. Yeah, I think you'll like it. It's not real long. Okay. The other assignment we're going to do after that is on earthquakes. Earthquakes. So I'm going to send you that one too. Let's talk a little bit about earthquakes. Are we going back to school next week? I wish I knew, Anne-Sophie. My guess is no, because I read that once they start us going back to school, us meaning students, they will probably start with the small kids this time instead of the big kids like you. So instead of older students, they may start with very young students and the Kitas. So I'll be surprised if we go back next week, but the Berlin Senat has surprised me before. So stay tuned, Anne-Sophie, and we'll find out together. I'd like to teach you live. On the other hand, I don't want to get corona. I'd like to get geimpft, as I'm sure you all would too. But for me, being an older guy, it's probably even more important. Okay. So if I have an earthquake, we know maybe that underground tectonic plates are moving. I hope you know that. So that's what causes an earthquake. So underground, here, let's just draw that. Here's one plate going under another. And let's say that one moves. Boom. If that moves, then boom, I get an earthquake right there. So this is a plate, and there's the earthquake. Earthquake. But if we look at, this is like a side view, okay? side view. And this is like the mantle, okay, the inner part of the Earth. And at the top was the crust. Okay, but that's all boring. Let's look at a top view. So bird's eye view, right? So you're looking down on an area. Bird's view. So here's the earthquake. Boom. Okay, just like we learned, like a pebble, boom, the earthquake will go out. But it turns out, so here's the earthquake, and it starts to go out this way. That's the wave. And that's called a, exactly. Yeah, we'll see. We'll see, Anne-Sophie. Okay. So that's the wave going out, but that's like called the P wave. The P wave means the primary wave. But there's another type of wave that starts at the same moment, and it's called the secondary wave. And I'd like to do that in a different color. Ha! There's my green. So at the very same moment, another wave goes out, but it's slower. That's why it's called the secondary wave. So here's the secondary wave going out in all directions. And that's the S, or secondary wave. So if you're out here, boom, let's say that's your home. What you're going to hear is you'll feel the P wave first, and they don't do as much damage. And then later you'll feel the secondary wave, and that does more damage. So feel P wave first, and then there's a lag, we say. A lag is an amount of time that goes by, as you probably know. Something's lagging. Then lag. Then the S wave. All right? So when you do the assignment on earthquakes, it's going to be talking about this lag time quite a bit. Now, there's a third thing that can happen if this is at the water. If this is at the ocean, what third thing can happen? So I got an S wave and a P wave if it's at the ocean. So if I got water above this plate, let's say I'm at the ocean here, what third thing can happen? Everybody jump in at once. I think you all probably know. You guys still there? Hello? So what third sort of wave can happen if it's got water above the spot where the earthquake happens? Yeah, a tsunami. Yeah, a tsunami, a tidal wave, they used to call it. Now they give it a more proper name because it has nothing to do with tides, by the way. So the third thing that can happen is a tsunami. But the tsunamis are much slower, okay? And you'll verify that in the exercise as well. Tsunami, water wave, could occur. I'll underline could because it sometimes will not occur. And these are slower. So the cool thing is, thank you. Folks did know that. Okay, I'm sorry it takes a little time for your answers to get to me sometimes. The cool thing is, after the P wave, then they start timing, and then when the S wave hits, they know how far away the earthquake is because of the lag time between the P and the S wave. And then if there's a possibility of a tsunami, they have time to react before the tsunami comes, probably hours later. Okay. The only time that doesn't work is when it happens right off the coast, like it did with Japan with the Fukushima nuclear power plant disaster. A tsunami started right off the coast, and of course there's not much lag time even between the P and S waves and the tsunami because it was right by the coast for the poor people of Japan. Okay, so the tsunami hit them very quickly. Just bad luck. But if it's further away, like Hawaii or something, from an earthquake, let's say at Japan, then the people on Hawaii would have time to react and prepare for the tsunami, a possible tsunami. They don't always happen, by the way. Okay, let me look, make sure you can talk about that. Good. The other thing this talks about is building buildings, like in a place like San Francisco, where there's a lot of earthquakes that happen because of the San Andreas fault. So imagine, we talked about this before, I think, too. Here's your skyscraper. And if the earthquake happens, right, so here's the earthquake, then that can cause a back and forth movement, right, with your building. So two things, your buildings have got to be flexible. Well, three things. Buildings must be flexible to withstand earthquakes. And you don't want the building to resonate. That would be a no-no. And you're going to investigate in the assignment on earthquakes how to avoid that as an architect. Okay. There's a third thing that is done with some buildings, most not, but some, and it's called a mass damper. A mass damper. And a mass damper is pretty cool. What it is I'll draw one up here. It's a really big chunk of concrete inside the building. And what they do is they make it sway in the opposite direction. So if it's going this way, they make the damper go that way. And then once it's going the other way, you know what I mean? It's like they try to counterbalance, and we would call that counterbalance interference. So interference reduces the swaying of the building due to wind or an earthquake. I'll write quakes. And I know that's getting hard to see. I'll read it off again. So this thing's called a mass damper, this thing up here. It's in some big buildings that have a lot of money, frankly. So what sort of interference would it be? Destructive. Thank you, Ellie. So it uses destructive interference to try and destroy the swaying, because you don't really want your building doing this. You want your building to not sway. With the wind is more common because wind is often present. Earthquakes are pretty rare, but that's the idea. So it uses destructive interference to send a opposite wave to destroy, right? Or negative interference, we also call it, to destroy the swaying wave from the wind or from an earthquake. Cool, huh? Okay, good. Ute, questions from you about earthquakes or bats? That's what's coming up for you at home. And if not, we're going to start something new. I believe I covered what I wanted to with you with sound. Let me take a quick look. While you're thinking, here's a fun thing. Aha, well, they must be well designed, Anne-Sophie. And speaking of Anne-Sophie, you mentioned playing the violin, and others may play an instrument, I don't know. But if you tune something, whether it's violin or a piano, what you want to do is use a tuner to essentially get rid of any difference in the waves. So if you hear a difference in the waves, it's called a beat, and you want to eliminate the beats. And there's a demo I could do, but I don't have it here at home. It's kind of cool, but I can't do it. So maybe if I do it at school sometime, but I've had problems with the Wi-Fi at school, as some of you know. You use your ear. And then so if you're using your ear, you're also probably mentally doing the same thing. Okay, good. We're done with sound. Let's begin with light in our last few minutes here. Okay? Let there be light. I'm going to show you an overhead first, but you're probably not going to see it very well. But I'm just going to give you an idea what that is, okay? So we're going to draw some of this, but can I point to it first here? I'm going to bring it close. Turns out there's a lot of light that you and I don't see, and that's why I wanted to bring this to your attention. Let's see. That's better. So look, here's all the different sorts of light, okay? Again, don't write this, all right? Just hold on. So we got radio waves, we got microwaves, infrared, we got visible, ultraviolet, X-rays, and gamma rays. And this is like increasing frequency, which we'll write on our notes in a little bit, decreasing frequency. And these are big waves, big wavelengths, and these are really tiny, tiny, tiny waves. Now, look how little we see. Isn't that pathetic? Check that out. There's the white part there is visible light. Ha! You and I are pathetic. Our eyes see very little of the total, what's called electromagnetic spectrum. And we're going to sketch a little bit of that now just to think about things, okay? All right, so that's the overview. That's kind of where we're getting at, okay? All right, let there be light. Okay, so let's take that down. And let's draw a little bit. By the way, we're up to like chapter 27 in the book. And you'll see that same drawing. So if you don't like my drawing, you can see it a little better in the book. Okay, let's do it the same way. So let's draw what's called the light spectrum or electromagnetic spectrum. Electromagnetic spectrum. In the spring, we may get to electromagnetic effects if we get that far once we do electricity. So what it means is light is a combination of electrical and magnetic waves. Weird. Light is really weird, as we're going to find out. But first, let's find out the types of light. So here we go. We're going to go this way. We're going to call it increase in frequency. Increasing frequency. And that's also going to be increasing energy. So the more frequency, the more energy. And at the very same time, that's going to be the opposite way. For increasing wavelength. All right, let's just sketch in some of these suckers, okay? So I'm not going to put a lot of numbers because we'll deal with that more later. Okay, so we got like the really big waves with big wavelengths are radio waves. Then a little less than that, we got cute little microwaves that we use in our ovens. We got infrared. I'm going to change that to IR. We have visible, which is just a tiny little thing. Visible to the human eye. And then we got ultraviolet, UV. We got X-rays. And then very high frequency waves are a type of radiation called gamma. You might have had that if you were here in what, ninth grade, gamma rays or gamma waves. Okay, these are all types of light waves. And let's start to go back and fill some stuff in. Radio waves are big. We're talking like tens of meters to kilometers long. But they're very low energy, and that's why they don't hurt you. Okay? Radio waves are okay. Radio and TV, okay, that sort of thing. Microwaves, like the ones in your microwave oven, these are like a few centimeters. They're cute little things. A few centimeters, okay? Visible light is in nanometers. So it's like 10 to the negative 9th meters. Oh, it's really small. Ultraviolet is less than that. We don't have to get into that. X-rays are around, what, times 10 negative 10? So 10 to the negative 10th to 10 to the negative 11 meters. And then gamma rays start at like negative 12, and then they go further back. Now, these are really, really, really small. Gammas are so small they like fit between atoms, okay? So they penetrate very, very well. Opposite, radio waves, they just kind of go through anything because they're so big, as it turns out. So, like I said, they're very low energy. These guys, gamma, can be dangerous because they have a lot of energy. So do X-rays. That's why you can't get a lot of X-rays. It's a lot of energy hitting your body, potentially bothering your cells, okay? Potentially damaging your cells. Ultraviolet still got a fair amount of energy. We worry about that if you're out in the sun too long. So that has a lot of energy that can damage skin. Infrared is less energy than visible, so that's not such a danger. Microwaves are special because they affect water molecules, so that's why they do their job, but we'll come back to that, okay? So my people, we've got a lot of light ahead of us. but that will start at least our ideas. We'll continue next week on ideas of light. But in the meantime, I'm going to send you one or even two assignments to work on, okay? And I'll have them do maybe one in the middle of next week, one at the end of next week. On bats, that'll be the first one I'll send out today, and then on earthquakes after that. Okay? Stay healthy out there, my four total physicist, and let me know if you have questions as you do them, all right? And I'll try and answer them. Okay, be well. See you soon.